Good morning. You're about to witness a world record because we're going to do 63 slides in 25 minutes. So, what am I going to talk about? Advances in scenario analysis. And there is scenario analysis which has to do with climate. Sorry, I have to point this way. Yeah. No, it's gone too many. I don't have to convince you that scenario analysis in climate is important. But when we talk about scenarios, we are, especially in the financial industry, accustomed to be giving scenarios without any probabilities attached to them. And practitioners tend to say, oh, I know how to handle these things. Why do I have to worry about giving me probabilities for this scenario? The fact is that in the case of financial stress tests or scenarios, or if I say 200 basis point shock in the yield curve or a fall in the index of S&P by 20%, institutional knowledge, experience, etc., gives us an intuitive feel for how severe the stress is. And if we want, we can do formal statistical analysis. However, if I were to tell the same decision maker, ask the same decision maker how severe a forcing of 3.4 or 6.8 or 1.9 is, this person, A, probably doesn't know what I'm talking about, and even if she or he does, has no idea as to the relative magnitude of these probabilities. So that is why climate scenarios are different, and the way the scenario framework has been set up at the moment has been completely probability agnostic. It's been a great start, but I think that we have to do something different. So the goal of what I'm going to talk about is how to associate probabilities to scenario outcomes. And this brings us to a key distinction: conditional and unconditional. What is the big uncertainty here? There is physics uncertainty, and we have had a beautiful presentation as tell us about the physics of the problem. But there is a great uncertainty, which is policy uncertainty. And how much we abate, how much we emit, how much we withdraw of carbon will obviously determine the outcomes in a very important way. So conditional is, if you tell me what the emission pattern is, I can give you a distribution of outcomes for climate. Then I can try to be a bit more ambitious and say, can we say something about the probabilities of these different policies? And that is what we're going to say. Obviously, it won't be sharp probabilities. We only want to talk about order of magnitude probabilities. So I am putting myself in the shoes of a policymaker, in the shoes of a financial decision maker, who says, which are the things I really have to worry about? Is it this scenario, or this scenario, or this scenario? So there are families of very well-established scenarios at the moment, which have been created by excellent academics, excellent quality work, but I am claiming they're probably not so suited to the needs, A, of policymakers, B, of financial decision makers, because they are totally probability agnostic, and that's what we're trying to fix. And I'll do a bit of description of why I find these type of scenarios wanting and what we can do instead. Having said that, these scenarios are widely used in the financial and policy-making community. So in trying to do something different, in one strand of our work, we are trying to keep as close as possible. We are trying to speak this established language as close, so to find a dialect of this language. And then we have also tried to do something which is a bit more different. We have done this by a radical extension of a well-known integrated assessment. So, first of all, obviously I'm not going to go through all of this, but this is just the structure. The current structure has 5 narratives. Narratives are shared socio-economic pathways. These are the ways in which demographics, population, GDP are supposed to evolve. They're very detailed. They're not in a derogatory way, but they're stories. They're narratives. SSP2 is called middle of the road. And that has been taken very often by as one of the most looked at scenarios. scenarios. I have to be very quick. I have to simplify things a bit. So these are the 5 stories. And how does it work? I have 5 stories here, and I have a certain number on the, it's like a matrix. On the x-axis, I have what is called forcings, which is watts per square meters. We can think about it imprecisely as temperature. There is a mapping which is not perfect, but it is a mapping between forcing and temperature. Think about it as, here I have a story, and here I have many temperature outcomes. And I'm trying to match these two. And there are these models behind, and these models, I calibrate the 3 parameters of these models in order to reflect the story as closely as possible. So in one story, there is high economic development, there is inequality, there is technological this type. I move all the dials so that my model looks like the story, and I have 1 degree of freedom left, which is the carbon tax. The carbon tax should be understood as taxation which is GDP neutral and which is completely devoted to abatement activities. And what I'm trying to find is, what is the carbon tax that I have to apply in order to hit the temperature, the forcing really, but let's call it the temperature. Story, temperature, 1 degree of freedom, the carbon tax. Here we are. Careful. Sometimes the stories are hardly compatible with some temperature targets. And actually, some temperature targets could be so aggressive, then given a story, you can't find the matching. You can't find the social cost of carbon that matches the two. But this is opaque, and the only thing that you can see is that sometimes the machine says does not compute. So you cannot achieve this match. But when you achieve a match, you have no idea whether the match was easily achieved, or was it just by straining the social cost of carbon in that. And we have looked under the bonnet or under the hood, depending if you're British or American, but we looked inside all these models, and we have taken them apart, and I'm going to show you what is behind the hood. A few observations. In the present scenario analysis, very strangely, climate damages play no role. And furthermore, agents do not react to higher temperatures, do not react to higher climate taxes. They're not optimization models. The only thing that you optimize is cost. So they're not the traditional economics models. And let me give, I've heard a lot of words. I think it's time to give you some pictures. First of all, these are the first feature is that all these models, given one story, they allow for extremely little variation. So here we're talking about scenarios. In scenarios, the first thing that I want to know, perhaps, is what is the dispersion of outcomes? What might happen if things go well, and what might happen if things go badly? Here, given a story, there is an extremely deterministic outcome for virtually all the variables. And I'll show you that for some it's very obvious. There is a population. If you read the story, it is very clear why the population is like this. But it's very, very, very stark, sorry, I'm getting the neck of this. Please go ahead. Okay, this is GDP. Same story. For each narrative, for each of the SSPs, I have one different GDP, and there is a typo there is GDP per capita per person, not per capital. But again, very, very inflexible. And you might say, people use different models. There are different, perhaps there is at least some variation coming from the models. When I put the same inputs in the different models, no variation at all. So this is a bit disturbing for something that is supposed to be used for scenario analysis. But there are more interesting things. Beg your pardon. Go ahead. I'm going to skip here. Here, it is the difference in energy mix for the 5 stories, SSP 1, 2, 3, 4, and 5. and with a difference with respect to the baseline. And there seems to be a lot of difference. So these scenarios are exploring really different things. But let's move one forward. Given one story, this is what the prediction is for all, given one target, 3.4, that is the forcing, all the different stories say exactly the same. Fossils have to fall like a stone, and renewables, and there are tiny, tiny differences, which I find unsatisfactory. And one more thing which I think is crucially important, which is the following. The carbon tax is sometimes disturbingly high. And I have put here I have SSP, so for SSP2, which is the middle of the road story, I've put different forcings. So from very low temperature, 1.9 is probably unachievable. 6 is on the high end of what Professor Chu was talking about. And in order to hit certain temperatures, the carbon tax is an astonishingly high percentage of GDP. 70%, 80%. It is for SSP 3.4, 40, 50, 60%, which does not look, let's say, fiscally possible. So all of these things are hidden. So we only discover them when we open the engine and we look inside. So the users, the consumers think, oh, I'm looking at totally plausible scenario. Well, I don't think there's a scenario with a carbon tax of 70 or 80% of GDP is doable. And furthermore, there is something else. GDP for the world, $100 trillion. Emissions of gigatons, 40 gigatons is not an equivalent. If you put equivalent, Professor Chu, it's higher. You do your multiplication, you say, if we have to put all of this into abatement, it would imply an enormous number of wind turbines and solar panels. In order to have something like the 40, 50, 60%, it will require the installation of 1 billion wind turbines per year. In the world to date, 300,000 wind turbines have been installed. So this is already telling you, well, mathematically everything has worked, but it doesn't make a lot of fiscal or technological sense. So here I am to do, first thing I'm trying to do is an SSPRCP is what I have described so far, which is the standard, which is everybody uses. And I want to try to create it, first of all, a distribution of outcomes, not a single path. And to assign some probabilities to these forcings and narrative combinations. So the process goes in 2 stages. And remember, we have taken 2 different approaches. This is the approach that stays as close as possible to what everybody is doing at the moment. We have to distinguish the baseline case and the case with policies. Baseline case is basically if we say we are not doing anything different from what we're doing at the moment, and the presentation before has told us what's going to happen if we don't do anything. And then there are the various policy options. And everything is expressed as the difference between the baseline and the policy. In the baseline case, I don't have to worry about the probability of the policies, basically because there are no policies. So that is easier. So let's begin from simplest thing. In the socio-economic narratives, they cover 3 aspects: the population growth, wealth, GDP per capita, and the technological development. And these are the quantities that appear in what is the so-called Buckeye identity, which I've compressed a bit. There are normally 3 multiplicative terms on the right-hand side. So it's the emissions. It is just an identity. It's like an accounting identity in finance. It's population times GDP per person times emissions per GDP. Now, the key observation, again, things that we have discovered by looking at the models of the SSP-RCP working, these are all so I don't know why it doesn't like me. they're all a very strong and clear function of GDP per person. So within the models, here we extract very strong relationships, for instance, about population growth and GDP per person, about emissions per GDP and population, which is linked to GDP per person, and again, emissions per unit of GDP and GDP per person. Plus there are residuals. It is a linear regression, I got residuals. And the residuals give me the dispersion I'm looking for. So what is the idea here? I simulate GDP per person, and I use the relationships which are embedded in the SSP RCP framework in order to work out all the elements of the chi identity. From that, I get the emissions. In the baseline case, I have no policy uncertainty. So that's the beginning. Very clear. So GDP, and this is a recurring theme. So just in a nutshell, what we are doing when we depart from this approach, instead of relying on the relationships which are in the models of the SSP RCP, we use empirical relationship on which we are working at the moment. And this dependence on GDP per person is extremely powerful. So the key insight is that if the distribution of GDP per person can be simulated, then I can have an unconditional distribution of the quantities entering the chi identity. So we can now depart from the specific narratives. I'm just using these narratives as points to use my fit. I no longer have to use the narratives now. I've just used them to get the relationships. We don't need the probabilities of these narratives because, important thing, you could have said, but Riccardo, why don't you do the following? Why don't you just apply probabilities to the 5 stories, different weights, and they will give you the dispersion you're looking for. The fact is that those 5 narratives do not span at all everything that can happen. So that in probabilities, they do not span the sample space. So I can't just give probabilities and say, I'm done. And by this, we can obtain an unconditional distribution. Now we have to introduce, what do we do when there is policy uncertainty? And here is one of the 3 empirical relationships, very strong, very stable, and very powerful, that we have discovered and that help us in this task. And picture, we have found that it is within the models, within the SSP RCP, the total emissions are given by the baseline emissions times some function of all the carbon tax you've paid up to this point. So emissions at time t are related to the baseline emissions, if I don't do anything, times this function of all the taxes has been paid up to this point. This is according to the models. And this is the strong relationship. So from this strong relationship, it says, okay, instead of talking about emissions, I can just as well talk about a process for the carbon tax. So the idea is, can I say something about the likelihood of carbon tax? And I said before, first thing that I can do is to put fiscal and technological constraints. Not everything can happen. And actually, it is quite extremely restricted. And second thing that I can say, well, for instance, one thing that I can say is that everything else being equal, ceteris paribus, the higher a tax, the less likely it is to be adopted. But the higher the experienced temperature, the more willing I might be to accept a higher tax. So these are 2, let's say, behavioral aspects that I can insert. And therefore, I can create a process for basically a tax process. And how do I determine the drift and the volatility? That's what I'm going to tell you in a minute with some empirical work that we have done about plausible distribution of policies. Okay, so this is what I've achieved, staying as close as possible to the existing framework. Now we take a bit of a departure. I'll come back to this. Building a more general scenario framework. Chi identity. Again, I've broken it down as is more customary to do into its 3 terms. But again, the observation is that each of these 3 terms is a very strong and clear function of GDP per person. So if I can simulate GDP per person, and there are varieties of economics models, Bansal and Yaron, so you name it, they can simulate these things. And therefore, if I have GDP per person, energy per GDP, emission per energy, I can reconstruct emissions. But now I'm going to be unshackled by the models of the SSP-RCP framework. I'm going to derive all these things from empirical investigation. So here's where we're going to proceed. This is Professor Tall has asked lots and lots of economists, what is your best guess for the optimal social cost of carbon, the carbon tax? And we could spend a full presentation on this. I'll go very quickly. It is a distribution of the opinions that have been expressed by these economists. So we have this, there is a distribution of social cost of carbons. It has to be fixed because some of the values reported are not realistic. Some people said millions of dollars per ton of CO2 emitted, which is, but let's, and furthermore and more important, these are the opinions of economists. Economists don't have to be re-elected next year. So we have to adjust for the fact that economists and politicians live in a similar but not identical world. And I'll show you how we can do that in a moment. So we proceed in 2 steps. Okay. Social cost of carbon is ultimately a tax imposed on the electorate. So take the world GDP, 100 trillion, take current emissions, 40 gigatons of CO2, and take a proposed carbon tax of X dollars per ton of CO2, you can easily work out that it is 0.04% of GDP per $1 of ton. Sorry, $1 per ton. So if I have a $100 per ton social cost of carbon, it is a tax of 4% of GDP. And to give a yardstick, current world expenditure at the moment is 3% on education, 3% on defense, 8% on health. It is just a yardstick. But I can say something a bit more. So my prior is, it is going to be politically not a non-starter, a carbon tax higher than what we spend on healthcare. You might disagree, you put a different value, but it seems to me I'm being generous. I'm being fiscally generous here. And here I have a picture. I have my 10th, 50th, and 90th percentile of log GDP per capita, so how rich I am on the x-axis, and the tax revenue as a percent of GDP. And the next one gives me my metric. So how rich I am on the x-axis and how much it is spent as a percentage of GDP. So when I do my simulation that is geographically differentiated, and if I had time, I'll explain why it's so important. So we have Africa different from, that's 25 minutes, I have to cut this bit, but X says, given each region, I can look, that region is that rich, they spend that much on health, and I'm going to say that the maximum tax that can be paid is no greater than what is spent on health. So this gives me a bound to the distribution. At this point, I can take 2 approaches. One which is very agnostic, says I just have a bound for the distribution. Anything is equally probable or possible within this distribution. I can do that. Or I can say, you remember that distribution of the social cost of carbons that the economists came up to? Well, that gives me a different likelihood for different social cost of carbon. But actually, how can I use that? That's how I'm going to use it. It is very difficult to say what is the probability of a policy. A policy is a path, is what I do to this year, in 5 years' time, etc. So what I do here, I have the blue line is an optimal abatement policy. When I'm at 1, I am completely decarbonized. Unfortunately, we're starting from there. And I'm fitting this with the orange curve. It's not a very good fit. I know how to do better fits, but this is not the point. So what I've noted, so the orange line is characterized by a single number. And what I've noticed is that all blue lines, which has the same fit, the same orange line, roughly produce the same temperature at the end. So I can characterize lots and lots of different policies by a single number, which is associated with the same temperature at the end. And beauty of beauties, so these are lots of possible abatement schedules. These are the associated smooth curves. And even a really crazy abatement, there is still a correlation of about 70% between the temperatures of the blue and the crazy curve. But here comes the really I have looked at a fantastically different type of configurations. Time separable and recursive utility functions, deterministic and stochastic processes for vectors. You can read it. I have really moved everything possible. And clearly for every configuration, I get a different social cost of carbon and a different optimal abatement, which is this number here. But there is an extremely strong relationship between the social cost of carbon and the optimal abatement speed, characterized by one number. That is a very strong relationship. So, if you have a distribution for the social cost of carbon, and it is a monotonic relationship, I can get a distribution for my aggressiveness characterized by a single number. So social cost of carbon goes to this magic number kappa. This magic number kappa contains lots and lots of policies that all produce the same temperature. Very nice. So if a distribution for the social cost of carbon, I have a distribution of policies, which is what I was looking at. So that's what I just said. These are the nice policies, the smooth curves. And please, this is just indicative. I wouldn't like anybody to say, oh, Professor Rebonato, this is his prediction. No, that is not what I'm saying here. But with a certain configuration, this is what I'm aiming to get to. A distribution of temperatures at a given horizon. So that now the decision maker can say, oh, these are the things I should worry about. The 4.5 in this configuration, it's a really a tail event. However, look, my expectation is 2.87. Not very different from what we were saying before if we do as continue as we are doing at the moment. And this is my aim, which I think it is a investment in policy useful way. So someone who is a policymaker, someone who is an investor, it is exactly the information that I think they're looking for. And 3 minutes, 0 means 3, right? Yes. So just very briefly, these are the empirical relationships that I was talking about before between all these quantities and GDP. Here we have a case of developed countries, and as you can see, emissions per GDP, emissions, energy per GDP, emissions per energy, US and UK, all a decaying function. Very, very nice, very clean. This is similar to the functions that you find in the SSP RCP. But look what happens with China and India. All of a sudden, we have strong regularities that can explain very well. In the early phases of development, the development is very energy intensive, and the energy is very fossil fuel intensive. And as society becomes richer, then there is a decline there. So the plan here is to get regionally differentiated, strong empirical relationships between GDP per person and all the key variables of the Kaya equation, get my probability there, and get the probability of policies from the distribution of SCCs. put everything together, and now it's 0. Thank you so much.